So, okay, ladies and gentlemen, welcome to our class. In the last class, we were talking about the internal energy. Today's topic will be mostly about enthalpy and heat transactions and degrees of freedom and equipartition theorem. Before moving to the next class, I would like to open up the last class topic and then remind you a few notations. So we have discussed about the heat and work as PV term. PV multiplication was yielding the work, and volume was the measure of the work, and temperature was the measure of the heat. So heat can be heat and work both are path functions, and they depend on the path you are taking in any physical or chemical process. That's why changing path when going from state A to state B does change the result of the work or heat, but the internal energy was a state function and did not change from state A to state B or any stationary states. It did not depend on the path. Okay, and heat, we described heat as the integration of heat capacity times dt, and result was when the heat capacity is assumed as temperature independent, the result was the Q is equal to the heat is equal to heat capacity times temperature change. So here Q is depending on the path, and C according to path is also changing. Okay, it can be a constant volume heat capacity or constant pressure heat capacity, and accordingly Q will be a constant volume or constant pressure heats. But the more important thing over here is that the Q and C, heat capacity and heat over here, are both extensive quantities. Okay, they depend on the amount of substance. So if we want them to be independent, we put molar heat capacity, and Q over here is molar heat. We can derive for per mole units. Okay, so this equation shows only for 1 mole of substance. So if we have more of substance, we have to include the mole number. Okay, and when we are talking about the 1 mole, we can also use little m over here to show this is a molar unit. Okay, so here C is the heat capacity and extensive property. So Cm is the C over N, which is the molar heat capacity. Okay, which now is an intensive quantity. Okay, so we can put either P or V subscripts to show that the heat capacity is measured at constant pressure or constant volume. So when we have such, for example, symbol, okay, I will zoom it a little bit so that you can see better. So when we have such symbol, the subscript P and M shows that the heat capacity is measured at constant pressure, and the heat capacity is given per mole unit, intensive quantity. Okay. So sometimes, occasionally, specific heat capacity is used. This is what you have seen in your high school class, probably. And specific heat capacity is the instead of per mole over here, now we use per mass. If it is per mass, we say this is the specific heat capacity, CS. Okay. Then you know the regular formula of a high school class, Q equals to M times C times delta T, right? m times c times delta t. We have learned this equation as Kerr-Majid. Okay. So, anyways, but in physical chemistry class, we are going to measure the heat capacities per mole mostly. And Cp and Cv are different from each other, and they are, depending on the path, affecting the result of heat that you are ending up. Okay, and heat is delta T times the heat capacity. Okay, this is fine. So the internal energy, total energy of system is called internal energy. This is what we have described. And internal energy was formed by the combination of kinetic and potential energy terms. And still internal energy is also extensive quantity. And to make it intensive, we put a M subscript. Sometimes people put a bar on top of it, okay? Especially the MIT course, where when you watch the YouTube videos or the MIT course videos, and they put a bar over here, okay, to show it's 1 molar or molar units, which is the intensive property. Okay. So we have discussed about state functions and path functions. That's fine. So anytime, according to the first law of thermodynamics, whenever we have heat and work transactions, so they are just components of the internal energy, the delta U, and delta U is formed by work and heat. Okay, and work done on the system, which is given by minus P delta V that we have already know. Any kind of formula in PChem, if you are talking about thermodynamics, you always put this formula and start with this formula. Okay, this is the very core of the thermodynamics, and this law shows the conservation of energy. Okay, change in internal energy is either work or heat, should be 0 when the system is isolated or isothermal. Okay, so the total energy of the system is constant. So anytime you see delta U that forms from W and Q, and for infinitesimal amounts, we use du equals to dw plus dq. Actually, dw was, there was a hat bar on this because this is not state function, right? You remember. Over here there was a mistake. I didn't include little bar, so it must be, oops. So, okay, let me like that. Okay, this is the accurate form. And dW was minus P dV, and dQ is we defined over here as C times dt. Okay. So over here, if the V is constant, delta V becomes 0 and delta U becomes QV, and we know that dQ over dt is the C, and now dQ was constant volume, and what we call this constant volume as the internal energy. Now we get a CV that is depending or delta Q over delta TV. So we can say instead of Q, we can replace with U because it's delta V 0. Now we can get the CV we can get the CV as delta U over delta T at constant volume. Okay, so the CV is described as the change of the internal energy by temperature. Okay. So if you remember from the first couple weeks, we were talking about kinetic molecular theory in which we derived this equation. We have found kinetic energy as 3 over 2 RT, right? So this is the kinetic energy term. When you assume that there is no potential energy, in ideal gas case, we assume actually there is no potential energy. So the total energy of the system is the kinetic energy plus potential energy. And this part is the kinetic part and there is no potential. So the total energy is actually this, 3 over 2 RT. So if we put this as the energy component, now the delta U over delta T was giving me the constant volume heat capacity. So if I replace this in the equation of this, now I will get the derivative of 3/2 RT over delta T. So I will end up getting 3/2 R. When we put the value of R, we get 12.5 almost joule per Kelvin per mole as the heat capacity, molar heat capacity at constant volume. Okay, so this is actually one example and valid for all ideal gases, but all ideal monoatomic gases. Okay, there is also different terms involved in when we have more than one atoms in the molecular system. So this is valid, for example, for a helium atom, for argon atom, for neon. This is mostly valid. Okay, but when it comes to nitrogen molecule or hydrogen molecule, for example, 2 hydrogen atoms, it's no more valid, and we have to re-evaluate this one. Okay, so this is valid for all monoatomic perfect gases, like this. Okay, so this is very important, and what you should actually learn about how you derive the heat capacity at constant volume or at constant pressure. We will come soon. Okay, so let's revise this again. Work is minus P external times delta V. When it's reversible, P external was the same as P system, and P system was, if it's perfect gas, it's easily to we can replace an RT over V and then delta V. So this is one thing, one extension to that, but this is the very general formula. And C is given by this formula. C can be Cp or Cv, we discussed. If it is Cp, it means the Qp, meaning that the heat at constant pressure, heat gained by the system at constant pressure over delta T. So this is heat gained by the system at constant volume. Okay, so delta U is this, and when it's isothermal, so the delta T is going to be 0, and the delta U will become 0. Okay. Yes. At constant volume. Don't remember that. Or isothermal or isolated systems. For isolated systems, there is no workflow, there is no heat flow, so that means that the delta U is also 0. So for an expansion, we have already said this one. when its external pressure is 0, the work has to be 0. Then heat has to be equal to the internal energy. When P external is constant but smaller than P system, if it is larger than P system, it's not an expansion, it's compression, right? If the P external is greater than P system, then the system, instead of expanding, the system shrinks. So it is a compression. But over here, P external has to be smaller than P system. If it is smaller than P system, which we call irreversible expansion, and which is given by this formula. It can also be equal to P system, which is what we call as a reversible process, and in which that we describe P system as nRT over V. And since it's nRT over V, integration on both sides yields the work as this one. Okay, so if we have expansion, reversible expansion, and isothermal reversible expansion of perfect gas is given by this formula. Work is this. Remember, since the isothermal process, the delta U is also 0. So this is a minus of this value, which is the plus sign, will be the Q. Okay. For compression, that is the opposite. The same equation yields, but the sign changes. Okay. So we have discussed these ones. Let's move on. So we have also discussed state functions. Okay. You will be asked questions about isothermal, isobaric, or adiabatic processes. There are 4 types of processes. They all can be both reversible or irreversible processes. They all can be a perfect gas or non-perfect gas. Okay, so there are 4 different processes. Each one can have reversible or irreversible processes, and each process can have perfect gas or non-perfect gas. Okay, so there are different, like 16 different possible operations that you can make, and there is also a compression versus expansion, so that complicates further. So for isothermal processes, which means the delta T is 0. Whenever we see an equation Q plus W, so we put delta U as 0 because delta U is only function of delta T. Okay, then Q must be minus W, and minus W we know that is equals to P times dV. For isobaric processes, for isochoric processes, which means V is constant. If V is constant, Q becomes QV. If it's QV, then delta U becomes QV plus W. Since the V is 0, W is also 0, and delta U becomes QV. Okay, this is the result of an isochoric process. For an adiabatic process, in which the Q is 0, so Q is 0, and delta U becomes W, which is minus PdV. And we know that delta U is CV times dt, so CV times dt becomes minus P delta V. Okay. For isobaric process, if it's P constant, Q becomes QP, delta U becomes Q plus W. Okay, so delta U now becomes QP minus P delta V if we assume this is a reversible process. Okay, and since the pressure is constant, we can take this pressure inside of delta sign. Okay, we can put this inside of the delta sign. So now it becomes QP, and take this whole thing to the other side of the equation. QP becomes delta U plus P delta V, and P we can put it in the other, and then we define QP with enthalpy. Okay, and delta H becomes now P times delta V, and so H becomes U plus PV. Okay, so this is how we derive enthalpy of the system. Let's come again. So we have been talking about the constant volume processes. Let's imagine the constant volume processes. So we can have some reactors that have constant size, doesn't change, but the pressure inside does change a lot because of the constant pressure, constant volume. But in real life, when we do experiments, we use beakers, and we all the time our beakers are open on one side, and the atmosphere pressure is always constant on any system that we are doing our experiments. Okay, so instead of having constant volume, which is not really common, because the volume constant means the pressure can change a lot. This is not very common in real life. That's why instead of writing the heat in terms of constant volume, we prefer to find another measurement that will be done at constant pressure. Okay, that constant pressure actually is yields us the enthalpy instead of energy. Okay, so the enthalpy is actually internal energy plus and PV term. Okay, so it is just like the energy. It is a heat transaction, just like the energy, but instead of at constant volume, it's a constant pressure. Okay, which is more widely used because experimentally all the measurements that we are doing is done at constant pressure. Okay, this is a very important, actually even more important than the internal energy, because this is something that we can have. We can measure lots of substances and their heats, and then report them at constant pressures, which will be actually corresponding to enthalpies. Okay, so this is for n mole, of course. For 1 molar, we can put the subscripts m. Some people put bar on top of them, as I told you earlier. So this is the molar and intensive quantities all. Okay, so Hm is equals to Um plus PVM. So since PVM is actually RT, right, in the perfect gas cases, so we can easily write this formula for ideal gases. Okay, so let's look at this nature of this new quantity, physical quantity, enthalpy. So when we have enthalpy, when we change the enthalpy by temperature, okay, that means this H was heat at constant volume, constant pressure. heat at constant pressure over temperature is given by heat capacity at constant pressure. Okay, and this is actually when we take the derivative of this whole thing according to T, we get delta U over delta T, and we get delta PV over delta T. Since its pressure is constant, we can easily take this out, or we can even write PV is equal to nRT over delta T. So when we take this whole thing as the CV, now we know Cp, and the derivative of this is going to yield as nR. For 1 mole, CPM, yes, for n moles, for 1 mole, CPM becomes CVM plus R. So, okay, we have found a relation between a constant volume heat capacity and constant pressure heat capacity, along with a new quantity, enthalpy, which is described as the internal energy plus PV term. Okay, so these are the new terms that are more relevant to what we are doing in chemistry and biology to do the experiments, because we are using open beaker system in our body too. All the reactions take place in constant pressure. Okay, a volume can change, the substance can fluctuate from one side to another, but the external pressure is always 1 atmosphere. And that's why using the heat capacity at constant pressure and the enthalpy are more relevant and more common, more standard, let's say. Okay, so Cp is equals to Cv plus R, we said. We also, above, we have described that for monoatomic gas, Cv was given by, where is it? Cv was given by 3/2 R, right? So, okay, if I know Cv, I can easily get Cp too, because there is 1 more R I will add, and 5/2 R I will get. But this is for monoatomic perfect gases. And what does that mean? In actually, yes, let's actually discuss what that can mean. So we have the energy of system. Let me put this on table. It's better actually. Okay. Tahtayı görüyorsunuz değil mi arkadaşlar?
Evet hocam, şu an görüyoruz.
Okay. We said that CVM is equals to 3R, CPM equals to CVM plus R. But this is for monoatomic perfect gas. Okay. Then CPM will become monoatomic perfect gas. Okay. So how did we derive this? We used du or dt at constant volume was C, right? Okay, and over here we put the h over dt at constant pressure. According to okay, let's imagine we have monoatomic gas. Let's say this is helium atom. Okay, so helium atoms in a system, there's more, and there is 6.02 10 to the 23 of them. There are this much of helium, which is 1 mole, right? So these helium atoms, we say between helium atoms there is no interaction. So the potential energy is 0. And kinetic energy is given by 3 over RT, right? And the total energy is this one over here, right? And delta U, let's say U total, let's say. Okay, this is molar kinetic energy again. And okay, we said this total energy of these molecules is given by this formula. Let's think about how these molecules can move along. Okay, what kind of motions that this molecule can have to have such kind of energy. Okay? If you remember from kinetic molecular theory, we said that molecules can have either x, y, or z directions, and 1 over 2 v squared, 1 over 2 this is the kinetic energy of the molecules, right? This does tell me that this molecule can either go from x direction, y direction, or z direction. So this molecule can move in all 3 axes with average speed of vx squared, vy squared, and vz squared. And their total energy is given by this formula. So that means that for each direction, if I assume the energy is evenly distributed, okay? If I say x, y, and z have the same exact energy distribution, then I have to divide into 3 parts. So this has to be 1 over 2 RT, this has to be 1 over 2 RT, and this has to be 1 over 2 RT. Okay? So if we have a system with some energy, any kind of energy, and we have some components of energy, the energy must be distributed all over the possibilities evenly. Okay? So you have energy E. Let's say I have energy E. I have 3 different possibilities, and the energy E must be evenly distributed all over the possible energy states. Okay? So now, since this is 3 over 2 RT, so this has to be RT, RT, RT. This is for 1 mole of molecules. So imagine that there is 1 mole, this many of helium atoms, and they will have 1/2 RT in the x direction, 1/2 RT in the y direction, and 1/T RT in z direction. So this brings a question that if we have more than one atoms, what is going to be the energy? So we can actually calculate what the energy will be for multiple atoms molecule, like diatomic molecule, let's say. Okay. So let me, before moving to that, so let's think about the helium atoms. Since these are single atoms and totally independent from each other, there is only one type of motion that these molecules can have, right? Which is called translation. Okay. So these molecules can go to X, Y, or Z. This is called translation. I draw, I think, Gauss view last time to show you what is a translation and what is a rotation and what is vibration. Did I show you? Let me show you again. Okay, I have helium atoms, let's say. Okay. So let me do this. Okay, as you see, what I can do, I can move this towards this way like that, or that way, or this way. So nothing more, right? So this molecule, all the motions that molecule, this molecule can have is called translation. Okay, all of the energy component is due to translation, right? So energy, potential energy, kinetic energy, translation. So X, Y, or Z. So any molecule will have this energy component. Okay? So assume that you have now, instead of one atom, you have two atoms. So assume that these atoms are like that. So what kind of motions this molecule can have? So this molecule can go to this way, this molecule can go to that way, right? So let's actually give numbers so that you can see.
Hocam tahta gözükmüyor.
Okay. Okay, I have this molecule, okay, now. Instead of one, let me repeat this again because you haven't seen. So I have energy, total energy, even I can show with U symbol, okay? I have U, and I have potential energy component and kinetic energy component. So this kinetic energy component has translation, which means that if I have single molecule, the atom, only this one. So this can go to this way, or this way, right? X, Y, and Z. So this what is called degree of freedom. So what is the degree of freedom of this molecule? It's only 3. It can go to X, Y, and Z. So for one molecule, degree of freedom is 3. So I am multiplying by 3. Okay? So degree of freedom is given by 3 times m. Okay? Nothing more. I can have no other energy term. This molecule has to have either potential energy or kinetic energy. This can't have potential energy because there is no other atoms around. There is no interacting anything. So this can't have potential energy. And this molecule will have kinetic energy. How many different types of kinetic energy exist? There are 3 different types of kinetic energy terms exist. But this molecule has single atom and it can only move around X, Y, or Z axis, which is actually called translational motion. Okay? So translational motion is X, Y, or Z. Okay? But what if I had, instead of one molecule, if I had two atoms molecule, like A and B. So now instead of, first of all, what is the degree of freedom? 6. What does that mean? That means that, okay, A and B. This is called direction. A can go to X direction, Y can go to the same X direction. A can go to X direction, Y can go to minus X direction. A can go to Y direction, B can go to minus V, or let's put Y. A can go to Y direction, B can go to minus Y. Right? What else? A can go to Z direction, this can go to Z, and this can go to Z, this can go to minus Z. So, and the same thing happens oppositely. So, A can go to minus X, plus X, minus X, minus X, okay? Minus Y, plus Y, minus Y, minus Y, and as you can say, minus Z, let's put it over here, minus Z, Z, minus Z, minus Z. So how many different types of motions that this molecule can have? There are 12 different motions, right? 6 plus 6, 12. But let's look at this one. A is going to X direction, Y is also going to X direction. So this is basically the molecule as a whole going and on X direction, right? This is actually translation. Okay? So A is going to Y direction, and B is going to Y direction. This is translation on X. Translation on Y. So, and this is translation on Z. If I assume these particles are completely independent from each other, these 12 different motions they could have, right? But among them, if both goes to x direction, this is called translation on x. If both go to y direction, translation on y. If both of them goes to z direction, this is called translation on z. And if both goes to minus x, let's say, so instead of this, now they will have this. So this is also translation on x. So actually they are both negative or positive. So they are moving either positive or negative. This is the same exact motion. Okay? So this motion, both of them are plus x or both of them are minus x, is the same motion. This is the same. Both of them y or both of them minus y, they are also the same motion. So I can actually exclude these minus terms over here because they are just repeat of what we have in x. Okay? So I have now both of them going either minus x or plus x, which is called translation on x. Both of them going minus y or plus y, which is called translation on y. Both of them going on plus z or minus z, which is called translation on z. Okay, what about these ones? What are these? Okay, so this one tells me that x is going this way, y is going this way. Right? This is actually what we call is vibration. Okay? This is called vibration. Okay? And this one, so this one is vibration. This one is also vibration. Right? This one is also vibration. So either going inside of each other's like that or outside like that. I will show you in this. Okay, so vibration, it can have only one vibration, right? And there is also one more thing that x goes to z direction, y goes to, or a goes to z direction, b goes to minus z direction. Okay, a goes to this direction, inside of the board, b comes toward me. What kind of motion is this? So x is going, okay, let me show you in this figure, which will be more obvious. Okay, I have now, instead of this, let's say I have this molecule, okay? Now I can have this motion, right? This is just translation, or this motion. This is also translation, or that motion on z-axis. This is also translation. So if I have two atoms molecule, I can have 3 translation, okay? But I can also have I can also have this one like that. This is called vibration. Okay. What else? So, okay. So this is a vibration, let's say. What else may I have? I can have X is going to Z direction, Y can go to like that. Okay. This is actually a rotation. So this rotation can be on Z axis like that or Y axis like that. Now this is Z axis, Y axis, and there is nothing more. So I can have this rotation towards me, or I can have this rotation towards the board. There are two different rotations. So this and this, actually, this and this are rotations. Okay. So I can have rotation. So for two atoms molecule, for two atoms, I can have three different translational motion, X, Y, Z. I can have one vibration and I can have two rotation. Yes. I moved on the board, but I haven't switched my screen. Okay. I am right here. Okay. So for my A and B, two atoms. So I told that this is a rotation and this is a rotation. These three are translations and this one is vibration. Okay. So for two atom molecule, for two atoms, I have three translations, X, Y, and Z, as I showed. I have one vibration and I have two rotations. Okay. So this is the degree of freedom. Okay, let's make this a little bit let's formulate this, okay? Instead of explicitly writing, let's formulate this. So we said kinetic energy has three components: translation, rotation, vibration. Okay? And I know if all the particles in this molecule were completely independent from each other, then degree of freedom is going to be 3n. Okay? In any molecule, three of the motions belong to translation: X directions, Y directions, and Z directions. Okay? Let's say plus rotation. When I had A and B like that, I had two rotations. Because I can have like that, flip like that, or I can have like that, right? Like that, or like that. Do you see? I can have a flip like that, or I can have a flip like that. Okay? So only two rotations for this kind of molecules. This molecule is a linear molecule. Linear molecules will have two rotations. And all of the rest of the motions are vibrations. So what is that for vibration? 3n minus 5. Okay? For a nonlinear molecule, I have still 3 translation. Now I can have 3 different rotations. So I will show you in this picture, actually, in the picture, let's work with an example. Let's add so okay, let me delete this. And I can build not benzene. I can have, okay, if I have such kind of molecule, now I can have a rotation on like that. Okay, this is X rotation. So this is Y rotation, like that, like that. Okay. Also like that. Like that. Yes. So this is another rotation. So there are 3 different rotations. So in X, Y, and Z. So if I have nonlinear molecule, I can have X rotation, Y rotation, or Z rotation. Okay? And then for the vibrations, it must be this.
Hocam yine ekranda bıraktınız.
I'm sorry. Evet arkadaşlar, özür diliyorum. For nonlinear molecules, I can have 3 translation, this time 3 rotations, and all of the leftovers from the total degree of freedom are the vibrations. Okay? So for example, if I have water molecule, how many is the degree of the freedom? 3 times 3, 9. There are 9 different motions that this molecule can have. Okay? 9 total different. If I assume all hydrogens, oxygens are all independent from each other, there would be 9 different motions. But I know 3 of them are translation, and 3 of them are rotation, and what is that? 3 of them vibration. So this molecule can have 9 motions, 3 times 3, and their motions are like this. Okay? So this is called kinetic energy components of the motions. Okay, now let's give 5 or 10 minutes of break. After that, I will discuss the equipartition theorem. Arkadaşlar 5 dakika dinlenelim, tamam mı?
Tamamdır hocam.
Ondan sonra şey anlatacağım. Şimdi bunu niye anlatıyoruz? Birazdan equipartition'a göre enerjinin bu şekilde farklı enerji bileşenlerine dağılımını göreceğiz arkadaşlar. Şimdi donduruyorum arkadaşlar. 10 dakika sonra devam edeceğiz.
Hocam geldiğinizde bu translation, rotation ve vibration'ı Türkçe'de bir kez anlatabilir misiniz?
Tamam arkadaşlar, döndüğümüzde anlatalım. 10 dakika ara. Merhaba arkadaşlar. Herkes döndü mü? Katılımcıları görelim. Evet, 32 katılımcımız var. Ses geliyor mu arkadaşlar? Ses gelmiyor sanki.
Geliyor hocam. Sesinizi
Geliyor mu?
duyuyoruz.
Az önce ne tartıştık, ne konuşuyorduk arkadaşlar? Bir molekülün sahip olabileceği serbestlik derecesinden bahsediyorduk İngilizce olarak. Moleküllerin birbirinden bir saniye toplam evet, şu an ekranımı görüyorsunuz galiba. Tahtayı görelim. Evet. Bir molekülde eğer molekülümüz ideal gaz gibi davranıyorsa dedik. Bu molekülde bir defa öncelikle potansiyel enerji ve kinetik enerjiden kaynaklı toplam enerji eğer monoatomikse potansiyel enerji katkısı 0 oluyor ve tüm enerji kinetik enerjiden kaynaklanıyor. Kinetik enerjiyi de molekülün motion, hareketi oluşturuyordu ve bu hareket ne olabilir tartışıyorduk. Bu hareketin 3 tür kaynağı var. Birincisi translation dediğimiz ötelenme hareketleri. İkincisi rotation dediğimiz dönme hareketleri ve üçüncüsü de vibration dediğimiz titreşim hareketleri. Yani bir molekülde olası bütün hareketler, motionlar, daha doğrusu kinetik enerjiyi oluşturan bileşenler bu üç hareketlerden kaynaklı oluyor. Şimdi molekül tek atomluysa helyum gibi, argon gibi, neon gibi işte tek atomlu molekül ise ideal gazsa daha doğrusu tek atomlu. O zaman bu molekülde rotation veya vibration'dan bahsetmek söz konusu değil. Çünkü bu atom yalnız bir tane atom. Başka hiç etrafta bir şey olmadığı için X, Y ve Z'de kendi ötelenebilir. Ve kinetik enerji sadece bundan kaynaklı kinetik enerji olur. Ama birden fazla atom varsa, mesela iki atomluysa dedik. İki atomluysa lineer molekül oluşuyordu. İki atomdan fazlada da lineer molekül oluşuyor ama en az iki atomlarda lineer molekül oluştuğu için bu molekül halinde X'de, molekül halinde Y'de ve molekül halinde Z'de hareket edebileceği gibi atomlardan bir tanesi X'e, bir tanesi Y'ye doğru gidebilir. Bu durumda da molekül, yani atomlardan bir tanesi X'e giderken diğeri Y'ye veya Z'ye gidiyorsa burada bir dönme hareketinden bahsediyorum. Atomlardan bir tanesi X'e giderken diğeri eksi X'e gidiyorsa ya da Y'ye giderken diğeri eksi Y'ye gidiyorsa bu durumda da titreşim hareketlerinden bahsedebiliyorduk. Dolayısıyla iki atomlu moleküllerde ya da daha genelleştirdiğimiz zaman biz bunu lineer moleküllerde her zaman için 3 tane degree of freedom 3n formülüyle veriliyor. Kaç atomluysa, molekül kaç atomluysa o atomu 3 ile çarpıyorum. Atom sayısını X, Y ve Z olmak üzere 3 ile çarptığım zaman toplam 3n tane farklı hareket elde ediyorum. Bu hareketlerden 3 tanesi her zaman translation'a gidiyor. Lineer moleküllerde 2 tanesi, non-lineer moleküllerde 3 tanesi de rotation'a gidiyor. Geriye kalan tüm hareketlerse arkadaşlar titreşim hareketleri. Tamam mı? Geriye kalan tüm hareketler titreşim hareketleri. Şimdi mesela orada suyu örnek gösterdik. Su 9 tane serbestlik derecesi vardır dedik. Çünkü 3 atomlu, 3 kere 3 9. Bunlardan 3 tanesi translation, 3 tanesi rotation, 3 tanesi de vibration olacak. Şu an tahtayı gördüğünüzü ümit ediyorum. Şimdi ben mesela burada bir tane size örnek olsun diye hızlıca bir calculate yapayım. Evet, önce şey yapalım. Test diyelim. Evet, birkaç dakika zaman alıyor ama. Bitti sayılır. Evet. Bitti arkadaşlar. Şunu açalım. Evet. Şimdi molekülümüz bu. Bakın 3 atomlu molekülde. Dedim ya 3 tane vibration olacak. Diğer 3 tanesi rotation, 3 tanesi de translation'dı. Bu vibration'lar nelermiş bakalım arkadaşlar. Bir tanesi böyle hareket yapıyormuş. Gördüğünüz gibi. X, Y, Z'yi de gösterelim. Evet. Mesela böyle bir hareketi varmış molekülün. Diğer hareket böyle bir hareketmiş. Üçüncü hareketi de böyle bir hareket arkadaşlar. Tamam mı? 3 tane vibration'ı var. Translation ve rotation'ları buraya print etmiyor arkadaşlar. Onların onlar da var. 3'er tane de onlar var. Toplam 9 hareketi var suyun. Şimdi enerjinin eş bölüşümü teorisi dediğimiz equipartition teoremi var arkadaşlar. According to this theory, I'm moving back to English. According to this theory, energy is distributed evenly all over the energy states. Okay, if how many doesn't matter how many of the different energy states exist. If this energy state is accessible, which means that if your total energy is larger than the energy level of this energy level, then you have to divide total energy into those states evenly. Even parts. You have to divide in parts. For example, okay, let's this part. So, equipartition theorem. Energy, total energy is distributed to all accessible energy levels evenly. Okay? So if I have total kinetic energy is, let's say, 3 over 2 RT, and I have 3 different motions, translational motions, then I have to say that 1 over RT is in each direction, in X direction, Y direction, and Z direction for okay, monatomic, perfect gas. Okay, so this is for 1 mole. If it was 1 molecule only, single molecule, then R would be replaced by K Boltzmann. Okay, so this is the energy component only on X direction. Okay, so for each allowed or accessible energy state, there is only 1/2 kT energy that is distributed in that state. So for each of the states, 1 over 2 kT energy will be in that state. So if we can find out what the total energy of the molecule is, we can easily calculate how much of that is distributed in each state by using this equipartition theorem. Okay? So energy, we said kinetic energy plus potential energy. Yeah, I can show with E also. Some show with E, some show with P. Or I can even say KE and PE. This is better. Okay? So this is always 0 for ideal gases. And for one monoatom, okay, U equals KE or equals translational E trans plus E vibration plus E rotation. So for monoatomic, there is no vibration and there is no rotation. So all of the energy is from translation, and translation energy is X, Y, and Z. So U equals RT. Okay. Then delta U over delta T R, which is a constant volume. This is called C. Okay. This is for monatomic, and this is nearly 12.5. Okay. Okay. Before moving to that, I will also tell you something else. Just a second. Yes. Okay. So if you know this one, let's say that the translation is related to 1 over mv squared, right? I don't want to confuse you a lot. Let's say translation has only kinetic component.
Hocam tahtayı görmüyoruz.
Okay. Just a sec. Okay. How about now? Okay. Translation has only kinetic component, and that's why for each motion, 1 over 2 RT contribution. Okay. For 3 translation, 3 times 1 over 2 RT equals to 3/2 RT. Or yes, that's because we know this 3. For rotation, it's kinetic energy contribution is due to the harmonic oscillations, which is again 1 over 2 RT, and depending on whether it's linear or non-linear, for each one, 1 over 2 RT times rotations. Okay. For vibrations, there is one term for kinetic energy, and there is one term for potential energy. So for each one, 1 over RT contribution exists. So for each vibration, there is actually one RT contribution. Okay? So for each vibration in molecule, there is one RT energy that will add up to the molecule. For each rotation, there will be 1 over RT contribution. For each translation, there will be 1 over 2 RT. Let's actually erase this one, okay? For kinetic RT, this is also in circle, okay? Translation in molecule, I will add 1 over 2 RT to the molecule's energy. I will add 1 over 2 RT for each rotation, and I will add 1 RT for each vibration. Okay? For example, if I have hydrogen molecule, okay? What is the degree of freedom of this molecule? 3 times 2, right? Do you remember? It makes 6. I know 3 of them translation, 2 of them rotation, 1 of them vibration. So for each translation, there will be 1 over RT, 2 RT contribution as the energy. For each rotation, there will be 1 over 2 RT. For each vibration, now there is 2, 1 or yes, direct RT, let me put RT. So how many different, or what is the total energy? What is the total energy? Let's put the total energy over here. U and So 3/2 plus 2/2 RT plus RT. Now that makes, okay, 7/2 RT. UN. Okay. So what is the CV? Seven half R. So what is CP? CV plus R, which is 9/2 R. Okay. So for diatomic molecules, instead of having 3/2R for the CV, we get a little bit more than what's expected. And this is because of the vibrations in the molecule. Okay? And that when we divide according to equipartition theorem, we can get about 7.5 R, which is nearly 29 joules per mole. This is 29 joules per mole. Okay? So let's do one last example. Let's say I have H2O molecule. What is the CV of H2O? Can we calculate this according to equipartition theorem? Yes. How? How many atoms are there? 3. And degree of freedom is 3 times 3 equals 9. So there is 9 different motions in this. Translation, 3. Rotation, 3. Vibration, 3. So for each one, 1/2 RT, and for each rotation, 1/2 RT, but for each vibration, 1 RT. Okay, total will make 6 RT, and CV 6R, nearly 50 joules per mole. Okay. This is what we have for the water molecules. Okay. So now in your exam or any other place, if you are not given a value of heat capacity for any substance, you can estimate by using this theorem. Okay, but this is going to be an estimation and not an exact value. The better values are actually getting, you can get them by doing the experiments. Okay, so you can change the, as we know, CV is actually dQV over dt, right? Or let me this way, Q over dt at constant volume. So you can change the temperature and by adding some heat, and then watch the system's temperature, and you can get the experimental heat capacities much more precisely. But if you don't have this experimental setup, you can estimate using this easy formula. Okay? So now I know that I have right DUM, DVM, and DHM equals to CPM times DT. Okay, and H equals to U plus P. I know these formulas. Now I can easily calculate C, and if I know the temperature change, I can easily estimate the energy change. Okay? So this is the end of this class actually. I have some other topic, but I don't want to enter today because it will be taking very long time. And on Saturday, we will do an extra class and we will cover this. Arkadaşlar, şimdi yeni bir konuya girmek istemiyorum. Bu konuyu iyice özümsememiz gerekiyor. Özellikle izobarik, izokorik, adiabatik, izotermal olaylar, expansion ya da compression şeklinde, reversible ya da irreversible şeklinde, perfect gas ya da non-perfect gas şeklinde bu tür olayların tamamını güzel bir şekilde yapabilmemiz gerekiyor. Ve oradaki hem enerjiyi, hem work'u, hem heat'i, hem de entalpiyi güzel bir şekilde hesaplayabilmemiz gerekiyor. Bugünkü ödeviniz de bu konularla ilgili olacak arkadaşlar. Termokimyaya da girmedim. Ama cumartesi günkü dersimizde inşallah termokimyaya da gireceğiz. Ve orada aslında bugünkü konuda anlatmaya çalıştığımız entalpi kavramının ne kadar önemli olduğunu ve reaksiyonlar için entalpinin ölçülerek listelenebileceğini ve literatürde var olan reaksiyonlar için entalpi değerleri kullanılarak bilinmeyen reaksiyonların entalpilerini tahmin edebileceğimizi göstereceğiz arkadaşlar. Hem fiziksel olaylar için hem kimyasal olaylar için entalpi değişimlerinin üzerine daha yoğun bir şekilde gideceğiz. Önümüzdeki ders inşallah cumartesi günü onu halledeceğiz. Şimdi bu konuyla ilgili sormak istediğiniz soru varsa alabilirim. Onun dışında bu konu bitiyor arkadaşlar. Burada bırakmak istiyorum. Yani yeni konuya girmek istemiyorum. Ödeviniz de buraya kadardı zaten. Yine de ders kitabına bir bakayım. Eksik bir şeyimiz kalmasın. Ders notlarımızdan eksik bir şey kaldı mı? Bu ders notları sizde var değil mi arkadaşlar?
Evet hocam, dosyalar bölümünde vardı. Eklemişsiniz.
Tamam. Tamam, buradan sonra artık kimyasal ve fiziksel değişikliklere giriyoruz galiba. Evet. Cumartesi günü bu konuyla bitireceğiz arkadaşlar. Dediğim gibi haftaya sınavınız var. Kitaptaki yani 11. edition olan Fiziko-Kimya Atkins'in kitabından ilk 2 chapter komple sınavda da olacak arkadaşlar. Yani quizde daha doğrusu. Soru var. Ekrem buyur.
Hocam bu tahtaya yazdığınız vibration eşittir hani kinetic artı rotation yazdınız da orayı anlayamadım ben.
Şey mi? Hangisini? Bir daha söyle. Nereyi?
Bu tahtada vibration hani eşittir kinetic artı rotation yazdınız ya.
Kinetik artı potansiyel. Hayır. Vibration'ın hem kinetik bileşeni var hem potansiyel bileşeni var. Bunu ders notlarında da görürsün. Ben aslında oradaki şeye girmek istemedim. Şu an ekranı görüyorsun değil mi? Benim ekranımı.
Evet.
Vibration için kinetik ve potansiyel bileşen var. Tamam mı? Yani biri yay geriliminden kaynaklı bir potansiyel enerji var. Bir de o yayın hareketinden kaynaklı harmonik osilasyon dediğimiz osilasyondan kaynaklı bir kinetik enerji var. Dolayısıyla her birisi için 1/2K geliyor. 1/2 RT geliyor daha doğrusu. Yani burada ben eski defterinizde bir molekül için yaptığım için KT olarak vermişim. Ama siz onu 1 mol molekül olarak düşündüğünüz zaman o RT arkadaşlar. 1/2 RT oluyor. Tamam. Bundan dolayı. Yoksa o rotation değil yani. Rotation ayrı. Rotation'ın burada. Rotation'ın burada arkadaşlar. Tamam.
Tamam hocam, sağ olun.
Başka sorusu olan var mı arkadaşlar?
Hocam quiz kaç soru olacak belli mi?
Quiz yaklaşık 30 soru olacak arkadaşlar.
Test mi olacak?
Sadece sözel işlem olmayacak quizde. Test, evet. A, B, C, D seçeneklerinden seçeceksiniz muhtemelen. Onu da Gözde hocanız hazırlayabilir. Emin değilim. Muhtemelen o hazırlayacak. Yani
Süresi belli mi hocam?
süresi 1 saat diye düşünüyorum ben ama 1 saat yeterli olur galiba. Diğer 2 saatte de ders yaparız arkadaşlar. Önce quiz'e haftaya geldiğiniz zaman önce quiz yaparız. Quiz'den sonra da ders işleriz. Cumartesi günü işleyeceğimiz konular quiz'de çıkar mı bilmiyorum, emin değilim. Sözel konular belki çıkabilir de sayısal zaten sormayacağız quiz'de. Ama sonraki hafta sınav arkadaşlar. Öyle. Başka sorusu olan var mı? Yok.
Hocam vize ayın kaçında olmuş oluyor?
İşte şu anda bir hafta geriden gidiyoruz arkadaşlar. Kaçında olmuş oluyor? 2 hafta sonra. 25'inde olmuş oluyor arkadaşlar. 11 şu anda. 18'i değil 25'i olacak. Tamam mı?
Tamam hocam.
Başka sorusu olan var mı? İsteği olan var mı? Şöyle olsun böyle olsun. Ben açığım arkadaşlar her şeye. Onu da söyleyeyim yani.
Hocam bu geçen haftaki soru çözüm videosunu biri kaydetmiş ama onu paylaşmamış.
Evet, onu kim kaydetti? Ben kaydettiğimden eminim ama bana düşmedi o. Yani hiç ortaya da düşmedi. Bir arkadaşımıza da düştüyse düştü ya da hiç kimseye düşmedi, bilmiyorum. Bilen var mı arkadaşlar? Kimde kayıtlı bu? Şeyde gözüküyor galiba, Activity'de değil mi? Chat historisinde mi? Activity'de mi? Orada gözüküyor olması lazım normalde.
Evet hocam gözüküyor. Kayıt da yapıldı ama işte biri siz yapmadığınız için başka biri yaptığında kaydetmesi lazım.
Ben anlamadım neden düşmedi. Geçen haftaki şey düşmedi. Video düşmedi. Evet. Ama soru çözümlerini ben siteye yükledim arkadaşlar. Oradan soru çözümlerine erişebilirsiniz. Chat var bir tane. Dur bakayım. Ebru günaydın. Tamam. Molada dersten ayrılan bir arkadaş. Tamam arkadaşlar, 34 tane katılımcımız var. Yoklama almıyorum. Sınıf tam gözüküyor. Başka sorusu olan var mı? Yani videoya ihtiyacımız yoktu. Geçen hafta Allah'tan uygulama yapmıştık. Onun için ihtiyacımız yoktu. Ama bir daha böyle bir hata olmasın diye hepinizden önce ben gireceğim ve kaydı ben başlatayım. Ben durdurayım mümkünse arkadaşlar. Siz müdahale etmeyin ona. Ya da bana hatırlatın en azından. Ben başlatayım yine. Yoksa başka türlü oluyor yani. Ben anlayamadım neden. Bir türlü optimize edemedik zaten bu şeyi. Şu anda da chat yazamıyorsunuz galiba. Onu da anlayamadık yani nedir. Chat'i de fix etmeye çalışacağız arkadaşlar. Tamam. Herkesin çıkmasını bekleyeceğim ben. Ondan sonra kapatacağım arkadaşlar. İyi günler diliyorum hepinize.
İyi günler hocam.
İyi günler.